Okay, I'm going to go through a couple of elevator problems. I already have them written out. All right. So, when you're on an elevator, the scenarios we've talked about, you don't have any horizontal forces. Okay, everything is vertical. So we've got normal. We've got normal, and we've got force of gravity, but they may or may not be equal to each other depending on your state of motion. If you're at rest in the elevator or if you're in a constant velocity, then they are going to be balanced. But if you're accelerating downwards or upwards in the elevator, then normal and force of gravity are not going to be the same. So we'll start with an example where we're accelerating downward. We have Captain America in an elevator. Here's his mass. Here's his acceleration. We want to calculate his forces. Okay. So force of gravity, pretty straightforward. Mass times G, 978 newtons. Then we're going to use net force to help us get kind of back into his normal force because we don't know that. Okay. We know that F net equals mass times acceleration. So I'm going to multiply mass by a minus 5 here because we're accelerating downward. So I'm going to take this value and I'm going to add a negative sign to it for direction. And then that gives me a minus 500, and I'm just using that in this calculation so that I have this downward direction included. So I'm going to set that equal to normal minus force of gravity. That's my vector sum of my forces, and we're doing it that way because normal is pointed upwards in a positive direction and force of gravity is pointing downwards in a negative. So then I set this minus 500 equal to normal minus my force of gravity that I got up here. I'm going to add this to both sides, and when I do that, I get a normal force of 478 newtons. So this is a case where normal force is less than force of gravity. That's what happens when you're accelerating downward. Yesterday we talked about apparent weight, which is what normal force is in this case. And so because this is less, you end up having a sensation of being lighter when you're in an elevator that's accelerating downward. Okay, and then our other scenario is accelerating upward. And so before I leave that one, here's my free body diagram, and I've got my normal force vector smaller than my force of gravity vector to denote this relationship here. Okay, now we're accelerating upward at 2.5 meters per second, same superhero, same mass. So we can use the same force of gravity we already calculated. And then we're going to use the same strategy. We're going to set F net equal to mass times acceleration. So we multiply those two, we get 250 newtons, and then we again set that equal to the vector sum, which is normal minus force of gravity. So now we got 250 equals normal minus this force of gravity. We're going to add that to both sides, and now we're going to end up with a normal force that's greater than our force of gravity. So when you're accelerating upward, normal is greater. That's kind of in my free body diagram. That one should be a little longer. This is why you have a heavier sensation when you're accelerating upward. This is your apparent weight, and since your normal force is greater than your force of gravity, your apparent weight is going to be heavier. So you're going to have this heavier sensation when you're accelerating upwards. Okay. But big takeaway from these two, when you're accelerating downward, your normal is going to be less than your force of gravity. When you're accelerating upward, your normal is going to be greater than your force of gravity. All right, so that was a quick overview on elevators.